Hello, this video will be a wrap-up of rectifiability of sets, where I will explain some applications of rectifiability and where they appear, and then direct you to an amazing channel where it has been studied in much more detail. First of all, the main article on Wikipedia about rectifiability is only the definitions. It's such a short and useless article there, unfortunately. The one on Encyclopedia of Mathematics, on the other hand, is quite nice. First, it begins by various definitions of rectifiability, which, by the way, is not universal among all texts. If you want to use a book or article for a reference, please do check what their specific definition of rectifiability is. It's more or less becoming uniform among authors nowadays, but older texts may vary. So basically, a rectifiable set, a quick recall, was a subset of a bigger Euclidean space Rn if there were countably many Lipschitz maps from the smaller dimensional Euclidean space Rk, such that the images of these maps, now they are subsets of the Euclidean space Rn, cover your set, maybe not all of it, but they cover it except for a set of HK measure 0. There are equivalent definitions. One of them is that you can actually take these Fi to be C1 maps, and that follows from the result saying that a Lipschitz map agrees with a C1 map on a big portion of its domain. And big portion being that the complement has a small, arbitrarily small Lebesgue measure. So in that sense, rectifiable sets are more or less just countable union of C1 manifolds. For example, the boundary of a square is a one rectifiable set. If you remove the corners, which has one-dimensional measure 0 anyway, the rest is union of C1 one-dimensional manifolds. We have done 2 complete playlists on area and co-area formulas. So those 2 big and important results are in their own enough to convince you that there is a lot of calculus that can be done on rectifiable sets, extending the calculus on Euclidean spaces or on manifolds. And in those series, I have given full proofs of both area and co-area formula. So I'll put a link to them in the description of this video, among a ton of other links that this video will have. Okay, then this article talks about some properties of rectifiable sets, and my favorite part, this criteria of rectifiability. So we saw, and I mean, we just mentioned this very deep and difficult result of Price, that if densities of a set exist almost everywhere, then that set is indeed rectifiable, a very surprising result. And the other one that we saw was Besikovich-Federer projection theorem. Indeed, it's fair to call it Federer-Mattila and Besikovich projection theorem in its full generality, because it identifies both rectifiable sets and purely unrectifiable sets based on the behavior of the projection of the set on almost every k-dimensional plane. To make this precise, one needs to know Grassmannian, and that there is some natural notion of measure on them, but anyway. Another one that I want to mention, and I'm glad it's here, is that in one dimension things are very special, even if you are in a metric space setting. If you are a compact connected set, simply from the fact that you have H1 finite measure, it follows that your set is the image of a Lipschitz curve. So here it says image of a rectifiable curve, but this rectifiability per definition is different. But I'm saying you that this is equivalent to saying that it's the image of a Lipschitz curve, which means that in dimension 1, you don't need extra structure, just finite H1 measure implies that your set is, plus of course the topological assumptions that it's compact and connected, that the set is actually image of one Lipschitz curve. And the details are in Falconer. We have done a full playlist on curves in Euclidean and in metric spaces. And there we also discussed this one. Okay, a more professional, say, place to look up is this survey from Mattila himself from last year, where he gives a survey of developments in the study of rectifiable sets. I want to show you some parts from it. My focus being just where else rectifiable sets appear rather than talking about new results. So the first instance he mentions is that sets of finite perimeter can be described by rectifiable sets. And more generally, I want to mention that there is this other result that in general BV functions, so sets of finite perimeter are those where the characteristic function is actually BV. But general BV functions have this structural theorem that they have jump discontinuities along a rectifiable set. So you can have, say, a C1 function here and then a C1 function here, which do not need to match up perfectly along this boundary. And the claim is that any given BV function has this set of a rectifiable set along which this happens, and in the rest of the space it's more regular. So that's the link between rectifiable sets and calculus of variations. The next one is that rectifiable sets appear in the study of minimal surfaces with the least area among all of the surfaces that span a given curve. So if you have a boundary curve, say, you're looking at all the two-dimensional, say, surfaces that span this curve, that their boundary is this curve. That itself is not quite precise definition. Just defining what we mean by a minimal surface itself is part of the problem. But results of interest are when you actually get a manifold, and it's well known that you don't always get a manifold. But then once you don't get a manifold, you're interested in the set of singularities. You can also do this with multiple curves. And a singularity, for example, looks like when two soap bubbles meet along a common boundary between them. So imagine these are very nice, smooth soap bubbles, but when they meet, they do it at some angle, which introduces the singularity. So Simon, he says in 1990s, proved some fundamental results on the rectifiability of the singularities, that the singularity, the set of singularities of such sets forms a rectifiable set of lower dimension. In complex and harmonic analysis, this actually is a separate chapter in Mattila's book. Check that for more detail, but he says that in his book it's still in a conjecture form, but because it was proven only in 1990s, as you can see here. So what David proved was giving an if and only if condition for when a set is removable for bounded analytic function. And a set is removable, so E is a subset of complex plane, we say it's removable for bounded complex functions. If for every function that is analytic and bounded on the complement of E, so for every such function, there exists an extension from all of C to C that is also analytic. Basically, that you can remove E in the definition of being analytic on all of C. And then there is connections to singular integrals when you have LP boundedness of singular integrals. So that's kind of a quick advertisement for usefulness and prevalence of rectifiable sets. I will share some more links to research talks, for examples, on the topic. There are 2 talks by Tatiana Toro, and there is Camilo De Lellis' talk. This one is about minimal surfaces. And then there is this PhD defense by Alan Chang. That was a nice one. I was listening to that one live. This is all from COVID era. The benefit is at least that we have such videos available. And last but not least is that Jonas Azam has this amazing playlist of 51 videos just focusing, not just focusing, but mainly focusing on rectifiability of sets. He goes through definition of Hausdorff measure, begins there with counter sets, self-similar sets. There's some overlap with what we did, but then he gets kind of deeper into main theorems and lemmas about rectifiability. He also mentions equivalent definitions of rectifiability as well. Very nice videos. I definitely recommend you follow up on them, and also do subscribe to his channel just to let him know that you liked his content. With that, I wrap up everything about rectifiability. I will turn to some other topic of hopefully again interest to you. Until then, have a great one, and thanks for watching this video as well. Thank you so much. Have a great day.